Thank you. So, that song will come back to us again during the talk a little bit. I'm going to talk a little bit about mathematics and music. So, my story is that I went to the University of Calgary to do my undergraduate, and part of the reason I went out there, certainly not in total, was I was also in a band, and it was very hard to break into the band circuit in Toronto, but out there, it was 1980. It was boom time in terms of oil money, and worked in bars from the very first week I came out. And I used to go to university there for my undergrad during the day, play in bars until 1 a.m. every night, 6 nights a week. Luckily for me, the first class at 9 a.m. was calculus, so of course I could sleep through that. So, at the end of my 4 years, I had to decide what I was going to do with my life. Music was going really well. I was playing constantly in concerts and things like that, and had done some songs that were playlisted across Canada. But I chose what I loved. I chose the safer gig, which was mathematics. But many years later, I brought my mathematics together with my music, and that's going to be part of the story. So, we'll see that mathematics can interact with music in a number of ways. Firstly, we're going to derive some mathematics behind the blues, why the blues are so great. One thing that I've been able to do as a mathematician, a tenured mathematician, is I can look at the questions I want to answer and ask them. And so one was, why are the blues so great? The blues are typically a certain chord progression, sequence of chords. Why are they the way they are? And that hadn't been asked before. We're going to understand the roles of patterns, transformations, and ambiguity in music. We're going to find out what machine learning can say about authorship in music. And we're going to use the physics of sound to deduce how a certain chord was played. Okay, so just to tell you a little bit about the mathematics behind music, pure tones are created by an object moving rapidly back and forth in a medium. So it's usually air, but it could be underwater as well. Pure tones are modeled by sine and cosine curves. This is the story that we should be telling students back in high school about why trigonometry is important. It's important for geometry and a number of other things, but everyone can appreciate music, and your ears and your minds are inherently built to hear sines and cosine curves. So more complex tones, and this comes to linear algebra, are linear combinations of sine and cosines. The speed of a pure tone is its frequency, measured in hertz, cycles per second, and it corresponds to its pitch, while the pure tone also has an amplitude, which corresponds roughly, not as closely as pitch does, but roughly to its loudness. So if you have a curve, a sine curve that repeats f times per second, you could model that by a times sine of 2 pi fx. Okay, so the first thing we're going to talk about, I had a question that was actually posed by that famous mathematician, Sir Paul McCartney. Back in the 1960s, a reporter asked him, what's the best rock song that was ever written? And does anyone know what he said? Yes. Long Tall Sally. We have never met before. Actually, we've met many times before. I'm lying. But yes, it is Long Tall Sally by Little Richard, who passed away not so long ago. And that's the song that we opened with. And there is mathematics strewn throughout it. But I realized that Long Tall Sally was an example of a chord progression. That's a sequence of chords that's called the blues. And everyone's heard of the blues. The thing about the blues, it's always the same chord progression. Almost always, just very small variations on it. It's always 12 bars, and when I say always, I mean almost always. 12 bars, certain chords last certain long. Once you choose the key, it's pretty much set. And now people spend their entire lives listening to the blues, and people spend their entire lives playing the blues. So I had a question, why are blues the way they are? It has to be something to make them so inherently magical, so inherently listenable that you could do that and you would still be thrilled by it. So we're going to play you an example of the blues, but to do it, I just want to make sure that we do it correctly. So I'm going to, unfortunately, I've got my sunglasses here, which have somehow come apart. Let me see if I can get them back together again. Okay. One last little touch, straight from Halifax. Okay. Let me. Okay, here we go. In A. 1 triplet, 2 triplet, 3 triplet. Thank you. Now, I just got to see where I put down my clicker. Yes, take off the sunglasses. That would help a lot. Got lots of pockets here. Let me just see. No, I don't take off my glasses as well. It's a curiosity. Oh, here it is. Okay. So let's talk about why the blues are so good. Now, the blues are always the same. A 1 chord, the major chord, in the key that lasts for 4 bars, the 4 chord, which lasts for 2 bar, the 1 chord, which lasts for 2 bars, then a sequence of 4 chords, each lasting a bar long, the 5 chord, the 4 chord, the 1 chord, and the 5 chord. The 5 chord is the most exciting chord. So let me explain to you why they're so good. It appeared in the notes of the Canadian Math Society a while ago. I had to think about what's the prototype of something that's so exciting in real life that you're willing to do it over and over again. And so I thought, well, what about a roller coaster? What about if I wanted to create a musical roller coaster that thrilled from the beginning to the end? So suppose we wanted to find a chord progression that's as thrilling as a roller coaster. I would build my roller coaster with 3 pieces, a beginning, a middle, and end, each of equal length. Now, you want the chord progression to be accelerating. You want to speed up as you go through it to make it more exciting. So the easiest way to accelerate something is to double the speed. So we're going to double the speed between the beginning, the middle, and the end. So if we're doing it harmonically, we would have 1 chord at the beginning. We should have 2 equally spaced chords over that space in the middle, and 4 chords at the end. And if you work backwards, the 4 chords at the end, if the basic unit is a bar, they're each a bar long. The 2 chords in the middle should each be 2 bars long, and the first chord should be 4 bars long. 12 bars, that's what the blues are. And 7 chords, exactly what the blues are. Now, you have to make some more deductions. So we want each chord between sections to be different, otherwise you don't sense any change. So you've got 7 chords repeating over and over again. I'm going to draw a line between, or an edge, between 2 adjacent chords, which I'm representing as nodes, or vertices. So what you get is a graph, C7. And now you want to color it, thinking your chords as being colors. How many colors do you need? This is a graph coloring problem. You can't do it with 2 colors. If you have to alternate, and you end up with a problem at the end. 3 colors is the minimum. So if we take our basic 3 colors as being the basic chords, the 1 chord, the 4 chord, and the 5 chord, then what we get with we use those, we can color the graph. Now we have to make a few more deductions. If you are building a roller coaster, you don't want to have your thrill at the beginning. You want it to be centered. You want to have the most basic chord, which is the 1 chord. And then you want to make a change. And what's the next chord that might be exciting but not the most exciting, because you want to save the most exciting part for the end? It would be the 4 chord. And you go along and make deductions along that way. What I came up with at the end is what I call a roller coaster coloring of C7. It's a unique coloring, subject to the rules of making an exciting, or the most exciting, musical harmonic progression, and the only answer is the blues. So I think the blues are mathematically built to thrill, and that's why you would listen to it over and over again. So here's an interesting question that I looked into. What makes the diatonic scale, which is the major scale, why is that sequence of semitones? 2 semitones, 2 semitones, 1. 2 semitones, 2 semitones, 2 semitones, 1. So why do you have that sequence as opposed to any other one? So I'm just going to explain some answers that have been offered by music theorists, which are mathematical in nature. The idea is based on the following. Suppose you're having a dinner party, and you have a round table, and much like the tables you have around here, and you've got 12 chairs, and what you're going to do is you're going to seat a certain number of people, k people around the table. You want them spread out as much as possible. How do you seat them? So what does it mean to be spread out as much as possible? If it's 6 people around 12 chairs, it's pretty obvious. Chair, empty chair, chair, empty chair. What about 7? So they came up with a definition of what it means to be equally spaced around a circle, a cycle in graph theory. A subset of k-selected vertices of the directed cycle of length n is called maximally even if every pair of selected points that have I selected points between them, the distance between them is either always the same number just based on I, or it's 2 consecutive numbers. So let me give you an example. This one is not maximally even. You can see it's kind of bunched up on one side than the other one. And if we look at the top and bottom point and go around the cycle in that direction, so it'd be, we're going around it clockwise, between the top and the bottom, there's 2 black points. The distance between them, graph theory-wise, is 1, 2, 3, 4, 5, 6. If you take the next point, the bottom point, and the one just before the top on the other side, they have also 2 black points in between them, but the distance is 1, 2, 3, 4. 6 and 4, they're not consecutive. So that's not maximally even. This is maximally even. You can check it. You have to do the check about how many black points are between any 2 black points and make sure it's always some number or differs by 1. If you start at the top and you label that C, and you think of the next one being labeled C sharp, then D, and all the way around, then the points represent C, D, E, F, G, A, B, the major scale. And so the theorem that they had was for every n and every k less than or equal to n, there's a subset of k vertices in the directed cycle that's maximally even. And it's unique up to a rotation, which means in music, you can start your major scale on any one of the 12 tones. And that's why the scale is, I think, the way it is. Now, here, what about if you had 5 notes? For 5 notes, maximally even would sound like this. And that's the pentatonic scale. It's the basis of much of the music in Japan and other countries there, and it's the basis of the blues. The 6 notes is called the whole tone scale. You might hear that in a movie if they had aliens arriving on Earth. And 7, as I played before, is the diatonic scale, the major scale. Well, the thing is that out of those, probably the least nice sounding is the whole tone scale. But it's the most even. It's between every 2 notes, there's 2 semitones. So why is that? Well, I think it's the principle, as humans, we like things to be perfect, but not too perfect. Okay? You probably know people that if they're too perfect, you probably don't like them. Anyways, so what about maximally even rhythms? So this would be an interesting question. You can do the same thing with rhythms by way you would strum. Here, if you have 4 places where you could strum, 4 beats, a maximally even example would be playing on beats 1 and 3, which are done in polkas. On 2 and 4, you get backbeats, which is the basis of rock and roll. I'm just going to retune here. Okay, good enough. That's the least interesting part, I assure you. Has to be done, though. Okay, we're going to do another example. Bossa Novas, which is one of the main music genres that came out of South America, is actually, it allows you, if you have 2 bars of eighth notes, so that's 16 eighth notes in 4/4 time, where would you strum 5 times? And it'll be 1 and 2 and 3 and 4 and 1, 2, 3 and 4 and nice and smooth and even. We're going to play you an example of that called The Girl from Ipanema. Okay. 1, 2, 3, 4. Okay, so, and we're going to do, what about things that are close to maximally even? You have the minor scale, which is the natural minor scale, which is the same as the major scale, just down a third. That's a fine scale to use, but what's used in Eastern Europe is called the harmonic minor scale, where you change one of the notes, just off by a semitone. It's even more catchy, I think. And, well, what about rhythms? So, I think that in mathematics, you're lucky and you feel wonderful if in your career they name a theorem after you, or they name a conjecture after you. Though I have to say, naming a conjecture after you is not as good, because I've had one named after me, and then in the Journal of Combinatorial Theory, someone wrote, the title was, The Conjecture of Brown and Colborne is False. So I have a title that has my name in it and the word false in it. So not as good as a theorem, but we're going to, if you're lucky in music, you get a rhythm named after you. So we're going to play you a rhythm called the Bo Diddley rhythm, which is almost a bossa nova, except one beat is off. And it has energy because of that. Bo Diddley. Okay, so patterns in music are the glue that holds songs together. Transformations on patterns allow for variety while maintaining consistency in the listener's mind. Composers have known this for centuries. We're all used to patterns, and we're all used to applying transformations to them. Certainly the basic ones of, it's called a music transposition, simply moving it up or down. But we have a wide variety of reflections, all those kinds of things available to us. We're going to play you some examples. The first example we're going to do is called I Walk the Line by Johnny Cash. Now, country music guitarists are known typically as 3-chord Charlies, because it's only expected they know 3 chords, the 1 chord, the 4 chord, and the 5 chord. And by the way, I played country music when I was in Calgary. It's not a term of endearment amongst musicians. It's something being close to like a Neanderthal on guitar, but it is true. So in country music, typically it is the 1, 4, and 5 chord. If you have other chords, it's unusual. How do you make country listeners who only used to basically listen to the 1, 4, and 5 chord accept it? So what you can do is apply transformation. So Johnny Cash plays a little line, and it allows him, by playing that line, doing transformations to it, essentially moving it up or down, that you accept the key change, which is unusual. So we're going to play you a little bit of this. 1, 2, 1. But it's not unique to country music, this idea of using patterns and transformations. Here I'm going to play a song written by one of the jazz greats, Duke Ellington, who took a little snippet, and that's what you can do. Take something that doesn't sound very musical. That's one little pattern, and then the other pattern is going to be this. And he's just going to take those two patterns, and he wrote a famous song by it, with it called Satin Doll. 1, 2, 3. Thank you. So we're going to play you one more song. This is by a mathematical group called Foreigner, which isn't a mathematical group, but they had mathematics in one of their famous songs. It's called Hot Blooded. You probably recognize it. If you don't recognize it, you're lucky, you're very young. So what they did was take something that, again, doesn't sound musical, like you couldn't make music out of it. That little pattern. But then they did a bunch of mathematical transformations on it. So they repeat it again. They move it up 5 semitones, which is a translation. They move it back in time, 2/8 notes. Again, a translation, but in the time variation. And then what they did was something, instead of playing, just doing it, moving up there, they put a mirror in their minds on the middle line, the B line, and reflected it. Again, very clever to use that kind of transformation isn't often used. And then they move it up later, 7 semitones from the beginning. So we're going to play you this, and they made $1 million seller plus out of this. Okay. So 2 bucks. 1, 2, 3, 4. I've always considered doing math rock and roll, and it is. Okay, so here's a quote, a quick quote for you. Which mathematician do you think wrote this? If you listen to the great Beatles records, the earliest ones, where the lyrics are incredibly simple, why are they still beautiful? Well, they're beautifully sung, beautifully played, and the mathematics in them is elegant. Now, if someone's recognize the mathematics in there is elegant, and that's a nice term to use. So who do you think said this? Not me. No? No? Stop repeating. Okay. So let's go. Here it is. The boss. So he recognized that there's mathematics in the music of the Beatles, and furthermore, it's elegant. Okay, so one of the questions I wanted to ask was, I knew that the Beatles were famous in England in 62, 63. They had lots of screaming fans. They couldn't break into America. American radio stations wouldn't play their music. So their producer their manager, Brian Epstein, got them a spot on the Ed Sullivan Show, which was the biggest show at the time, a variety show. And he told them, lads, you're going to play on the Ed Sullivan Show in 6 months. And by the way, you have to come up with a great new tune to open up America. And this is like, think about you come to a conference that's the biggest conference of your life in 6 months, and someone says, oh, by the way, come up with some new research that's groundbreaking, that will be the biggest research not only in your lifetime, but maybe in everybody's lifetime. Okay? The Beatles rose to the occasion. They wrote I Want to Hold Your Hand. It's a great song. And how did I want to know how they conquered America with that one song. The lyrics are terrible. Oh yeah, I'll tell you something I think you'll understand. Oh yeah, I'll tell you something. I want to hold your hand. I want to hold your hand. I want to hold your hand. Okay? Not brilliant, but the music is brilliant. It's also, the melody has only notes in the key, in the major scale. Now, what songs typically have notes just in the key? The blues songs, if you have a typical rock song, it has notes outside of the key, maybe the flat third from the blues or the flat seventh, but not just in the key. So what songs have notes typically only in the key? Nursery rhymes. So why, by all reason, it should sound like a nursery rhyme, but it doesn't. It's the mathematics that I think is inherent in it. It also sounds fresh. I've listened to the songs hundreds of times, and every time I find it exciting. And again, I think the freshness in the song, when I listen to it repeatedly, is the mathematics. So I'm going to talk about this in a second. We're going to play you a little bit of the song. Oh, something's a bit out of tune. Hold on. There we go. Okay. Sorry about that. I have to retune. I hate being out of tune. Okay. So here we go. Right. So we're doing one verse and then the bridge. 2, 3. Thank you. So I want to tell you a little bit about the music and the mathematics that's inherent in the song. Ambiguity. So you would think that ambiguity is a bad thing, and it is a bad thing in relationships. If you have a significant other who plays guitar and writes songs, and she says to you, what do you think of my song? And you say, I'd like nothing better. That is a bad choice of ambiguity, and will get you at least hours in the doghouse. In music, ambiguity, though, is attractive because it allows you to listen to something over and over again and appreciate the ambiguity, appreciate the paradox. So we as mathematicians embrace ambiguity to translate a problem from one area of mathematics into another, or to look for alternate models of a theory. So let me explain to you. The beginning seems pretty simple, and composers embrace ambiguity for interest. The beginning of the song sounds pretty simple. I'll just play. So why is it so interesting? It is interesting. So the thing is, as listeners of popular music in 4/4 time, which is the typical bar signature, 4 beats in the bar, we orient ourselves to beat 1. And we want to know in our minds, where's beat 1? So and without any other ways to determine it, you assume the song starts on beat 1. So you assume this is 1 and 2, 1 and 2. But it's not. And you only get the joke that you've been fooled when they come back, oh yeah, I'll, and that's definitely beat 1. So what they do, the Beatles, those great mathematicians, is they apply a transformation to it in time, x minus 3. They move everything back 3 eighths notes. So it's 3 and 4. And 4 and 1 and 2 and 3 and 4 and. And therefore, because you're tricked every time, it's like the two faces in the urn. Even though I know this, I'm tricked every time, and you get that little bit of a joke. Now, another thing that I'm going to talk about is there's the modulation from the key of G to the key of C. They changed keys, which was unusual at the time for a rock song. So that's in the bridge. And when I touch you, I feel happy inside. Strange chords. It's even got a D minor 7. That's outside the key of G. So interesting chords. And I wanted to figure out, why is the bridge so good? Why does it fit the song so well? And yet, it sounds fresh. So the chorus goes C to D to G to E minor, C to D to G. The bridge is D minor 7 to G to C to A minor, D minor 7 to G to C. In the chorus, each chord lasts 2 beats. In the bridge, they last 4 beats. So the chords, how do they make sense? But a D minor 7 is D, F, A, C, so I have to rely on a little bit of music knowledge here. It's essentially the same. F, A, C is an F chord, but with it just has a different bass note on the bottom, a D. So really, what's going on is if you replace it by what it really is an F chord, you get the same pattern. It's the 4 chord in the key to the 5 chord to the 1 chord to the 4 chord to the 6 minor chord to the 5 chord to the 1. The chorus is the same chord sequence as the bridge, but they did 2 transformations on it. They moved it up 5 semitones, and they stretched out double in length. So that should have answered it. Okay, that's why the bridge chord sequence fits the song so well. They did 2 mathematical transformations on it. Now, the other half of it is when they did that, the right chord is the F chord. They play a D minor 7. The D minor 7 is the right musical chord. It's more musical than the F chord. The F chord is really out of the key of G, but the F chord is the mathematical one. So I want to see what they did when they played it. Now, I had 3 articles published in Guitar Player magazine as a mathematician. I think I'm the only mathematician to have published there. One of them was called The Mathematics of John's Left Hand. And I'm going to play for you the video for when they played it. This was the first time they ever played the song. Watch John's left hand if you're a guitarist, and I'll explain what happens afterwards, when they come to the bridge. You let me hold your hand. I want to hold your hand. And when I touch you. So the thing is that John is playing the F chord. It's clear that George Harrison's playing a D minor 7 and Paul is playing a D in the bass. Why is John playing a different chord? It's unusual for 2 guitarists in the same band at the same time to play 2 different chords. You agree on the chords. That's what you do as a guitarist. So the thing is I think John was the kind of personality who said something in his mind like, forget that, and I'm going to play the right mathematical chord. And that's what he did. So I'm going to give you a little bit of explanation here. This is from George Harrison's autobiography, I Me Mine. He wrote all those logarithms and square roots, and algebra was a terrible thing. X plus 3 over z equals y. So you can see there's real math problems here if he's forming a fraction with z equals y in the bottom. I would have learned Chinese or Sanskrit sooner than that. It seems to have made sense to the academics, the intellectuals. Algebra, I have no idea what it means or where it came from, but algebra to me had nothing to do with reality. I watch it now on Open University and still can't connect. The amazing thing, this was written after the Beatles. You've got someone who has as much money to do whatever he wants in the rest of his life. What is he doing? He's sitting at home watching math lectures from the Open University. And I think that's because he understood that mathematics played a role in his music, but didn't know why. So we're going to play an example. There's a mathematical trick that George loved. It came from Chuck Berry. And it's when he did his duck walk. And it's patterns of 3 against patterns of 4. So I'm going to kind of nod when I do it. I'm too old to do a duck walk. So I will just sort of move around, but I'll nod when I come to it. 1, 2, 3. So it's those, thank you. It's those 3s against 4s that are so energetic, so moving, that even though Chuck Berry did it in his head, it made him move emotionally and physically. He did his duck walk. So lots of people have been attracted to it. They probably don't realize what they're doing. You have to do a least common multiple in your head to get out of it. 3 and 4, because basically the patterns are 4s. It's 12, so you play 4 patterns of 3, and they equal 3 patterns of 4, and you get out of it. So you have to do that in your head. So make the trick work, you need an escape hatch to know when to leave, and that's with the LCMs. So we're going to do an example here. I wrote something, so that's patterns of 3s versus patterns of 4s. I wrote something with a riff that's a little bit of music on patterns of 5s. And that's a little piece of music that I wrote. I decided that those 5/8 notes I would repeat 3 times, have an extra note afterwards, and that gives me 16 beats. I had professional musicians play along with me. They've been playing for 30 years. They had trouble playing it. What I had to do as a mathematician, I decided it will sound good. I wrote it. I taught myself it till I could play it, and now it's natural. So I'm going to play a little bit for you. It's a 5 against 3 blues. Okay, so do it around twice. 1, 2, 3, 4. Thank you. Trying to be cognizant of the time here, but it's running out. George Harrison played patterns of threes in his famous solo from A Hard Day's Night. You can see that there in the F chord, very fast. What I figured out is so perfect that he must have cut the tape speed down in half. And I found one of my articles I wrote in Guitar Player magazine was exactly that. What he did, it was too fast for him to play. He cut the tape speed down in half. Mathematics of music tells you then notes go down the octave. So he played it down the octave, half the speed, and then they cranked it up. I'm going to skip a little bit of this because I want to get to the end of my talk. But one of the things that I found out is he couldn't play it live after that. He had done what it took to get it played. He couldn't play it live to tape on the BBC, and they had to cut it in from the record at that point. He had to mime it. A week later, he learned to play it. A beautiful mathematical story about someone who let the mathematics of music drive his playing, not what his hands could play, but the mathematics drive it, did whatever it took afterwards to be able to play it. Okay, so I'm going to talk a little bit about In My Life. A famous song by the Beatles. And it's the one song they asked John and Paul, who wrote the song afterwards, because they typically wrote the song as Lennon and McCartney. All the songs are Lennon and McCartney, although only often one wrote the song. I'm not going to read through all of this. They asked in Rolling Stone, everywhere, who wrote the song. John said he wrote the song, and that maybe Paul helped afterwards. And then Paul said, no, I wrote all the music, and I gave it to John to put the lyrics to. So who is right? So I wanted to use machine learning and data science to figure out who likely wrote the music. So I got together with Mark Glickman, who's a statistician at Harvard, and he had a student. And so what I did is I collected by hand all the music, note by note and chord by chord, of the Beatles up to the end of Revolver. I think it was 6 or 7 albums. And used all that data, and I collected what notes were played relative to the key, sequence of 2 notes, chords, sequence of 2 chords, and the contour of 4 successive notes in the melody. We got lots of data here, and we had 137 categories, and we had to figure out which ones were important. And so we looked at these. We actually used some statistical techniques to find out which features were important. We brought it down to 37. We did some analyses of this, and we'll talk about that in a second. So we found out John uses the 1 chord to the 5 chord, to the 6 chord more often. McCartney uses the 2 minor to the 4 chord. So there's some things we found out that we might not necessarily hear when we're listening to their songs. So I'm just going to move ahead. We used logistic regression after eliminating features. This is what we got for our predictions. The red are John's songs, the green are Paul's songs, and it tells you what's the probability for each song of who wrote each song. And as you get for some of the John songs, they're very a lot of them are 0 in terms of Paul authorship. So we looked at songs or parts of songs that didn't have clear authorship. When we came down to In My Life, it was a surprise to me, but what John recollected was closer to what we found. that it's much more of a John song, clearly in the verses, which is what the left side. On the right side is the bridge, shows some influence of Paul. So maybe that story was correct. Of course, the media wrote, Paul misremembers, which is not what I said, but the media takes it. They weren't interested in the real math behind it. They want the easy headline. It's just more in John's style. Maybe Paul wrote it in John's style. That was possible. So I'm going to quickly talk about one more song, which is where my road in mathematics and music started. It should be updated. At the time, it was 40 years since A Hard Day's Night was released by the Beatles, and the film began with one of the most famous chords in rock and roll history. You ready? 1, 2, 3, 4. Okay, so let me tell you quickly the story. I'll be going over a little bit. I have to warn you, but you need to get to the end of the story. So that's the opening chord from the Beatles. The producer said we knew it would open both the film and the soundtrack LP, so we wanted a particularly strong, effective beginning. The striding guitar chord was the perfect match. But is that the end of the story? There are various ways the guitar chord is written in transcriptions. That's one, not so good. That's another one. And here's one transcription has all three Beatles. How do you decide? Well, I thought, what about using mathematics to decide? You can use Fourier transforms to decompose the opening chord into its constituent pure tones. So I got a beautiful picture, which is this table of the 48 frequencies of largest amplitude. You find things that you expect there. 110 hertz is a low A note. So that's a guitarist can play it. And one thing you notice from the numbers is they should be, when you convert them over with a log function, because that's how you have to do the conversion, you find out how many semitones they are away from a particular note. It should be an integer number. But some of them, like minus 6.7, isn't an integer number away. What's going on? The beauty of the chord is I can tell that no one else can tell. They were out of tune by the time they recorded it. And that's why you can't reproduce it. They couldn't even really reproduce it. The producer should have knocked on the window and said, lads, tune up again, but he didn't. So I can see they're out of tune. The other thing I notice is that there's no low G note, which is in all the transcriptions. They hear it, people hear it, they know it's in the key of G, they think it's there, but it's not there. So I tried to make deductions that there's a loud D note, it's obviously the bass. I got stuck with the rest, and I couldn't figure it out. I knew George Harrison played a 12 string like Mark's playing, but I couldn't figure out, in particular, there was an F3 that appeared 3 times. There's no F4, but there should be an F4. And then I figured out, I have a hidden assumption like we do in mathematics. Maybe it's not just the guitars. Maybe there's a piano in a mix. Maybe there's a piano that's known to play on the solo, double the solo, in the mix at the opening chord. That unraveled it for me. Pianos typically have 3 strings under each note, at least from the middle upwards. That was the solution. And so I came with some notes that I attributed to the piano, which was undoubtedly played by George Martin. And then George Lennon played a note on the 6-string guitar. This is the chord that I wrote for the Guitar Player magazine. Terrible time getting it published. I sent it to Rolling Stone ahead of time. They said, they kept it for 3 months. They said, I said, well, what do you want to do with it? They said, this is great, but it has mathematics in it. We can't publish it with math in it. Then Guitar Player magazine came to me and they said, we love it, can you take out all the math? And I said, no, you can't take out the math. It's like a Harry Potter novel, magical without it. So they let me keep some of it. So, the producers who said it was a great guitar chord undoubtedly played the piano on it. So what's going on? I call this Martin's axiom. The producer was George Martin. It shouldn't be expected that people are necessarily doing what they appear to be doing on records, he said in his autobiography. It's like someone jumps through a plate glass window in a Bond movie. The producer doesn't come on and say the actor is fine, right? You have the illusions. So there is a sad part to the story. I hope you can commiserate. It was on the national page of one of Canada's national newspapers, the front page. You think the one time you get on the front page of a national paper, they would use your picture. So my brother was in Toronto. He was on an elevator with someone who knew him. He said, I read the article about your brother, and by the way, I can't believe how much he looks like Paul McCartney. So after that, I was approached by a literary agent. I wrote a book for the general public, as Brett mentioned, Our Days Are Numbered, How Mathematics Orders Our Lives. The story is in there. The story is in as well. I wrote a book, Mathematics for the Liberal Arts. It's based on telling students stories surrounding different parts of mathematics. I tell the story of my discovery of the opening chord. It's got regular, the usual things that you expect from math for the liberal arts, but there are stories at the beginning and end of each chapter. I do have some free copies that I can give out after the talk. I do have some flyers if you want to purchase it from the publisher, CRC Press. I thought of sending out the free books, getting one of those t-shirt launchers, maybe for textbooks, but I thought that's probably a bad idea. So that's probably why they haven't invented it. I did my album, Songs in the Key of Pi, and if I can just take a few more minutes, Wall Street Journal came up to interview me about this. They came up to Halifax, they sent a videographer. I said, well, I've written a song using mathematical principles that I gleaned from their work. If I get a band together, will you film it and record it? And they said yes, and then I panicked, had to get a band together. But we did record it. It's a song I wrote called A Million Whys. I tried to write it as if it were would be a hit for the Beatles in the early 60s. There are a lot of little mathematics that I found in their music that I tweaked, that I extended. I'm going to talk about that more in the paper session, but have a listen.
She's got a million reasons leaving you some other guy. She's got a million reasons. I got a million why. Have a million purges, swallowing all of your lies, Yes, she should have a million purges. I've got a million wives. I'm so sick and tired of hearing how she loves you. So sick and tired getting tired of hearing how she loves you, loves you. I can't wait for this bubble to burn. I see you got any reason leaving you some other guy, for any other guy, for any other guy. See, you got a million reasons. I got a million why. Got a million why. I got a million why. Got a million. Yeah, I got a million why. Got a million why. I got a million why.
Thank you very much. Pleasure to be talking to you. Just want to thank Mark on guitar, Mike on bass, BD on drums.